All right, we'll go from current slide. And before we get going, give you both these set of announcements. The college fair, okay, and also the research experience for undergraduate poets, okay, right. Make sure, especially you guys, hear about that kind of stuff. Okay. Now, where we left off last time was Chapter 1, Systems of Linear Equations, Section 1.1, which I hope we will finish today. It's a long section, but hopefully we'll finish it today. And it's Introduction to Systems of Linear Equations, and we have done through example 6, and we were just at the top of page 7. Now, what we did last time was solve a system of equations that was very easy. It was that triangular system, you might say, backing up, and we had done that. I think we did it at the top of the page, not realizing that was example 6. So, any questions on anything we've done so far? All right. Now, I told you before the things at the top of page 6, those two systems of equations are what we call equivalent systems because they have the same solution. Okay? It was real easy to get the solution for the right-hand side one. That's what example 6 was. But the left-hand side, it wouldn't have been nearly so easy. Now, what we're going to start with today are operations you can do with equivalent systems that keep them equivalent. Okay? In other words, these are things you can do with any system of linear equations that produces an equivalent system. 3 things that you're allowed to do. Oh, well, that may be because I haven't turned on the projector. Okay? I don't know why it won't turn on when I want it to be on, but it just doesn't do that. Okay? Maybe it doesn't like reading. Never mind, my mind. Okay. All right. It's coming up then in a little bit. So these are the 3 operations. I hope it's coming up, and there it comes. That will always produce equivalent systems. Okay. So you have system of equations. So many equations, so many variables. Okay? Maybe equal, something equal on the other side. So here are the 3 steps you can do to produce equivalent system. First, interchange any 2 equations. Of course, hey, what difference does it make what order they're in? It doesn't. That is a good first step. Interchange any 2 equations. All right? Secondly, multiply any equation by any non-zero constant. Now, why wouldn't you want to multiply by 0? You lose the meaning of everything, okay? So yeah, never multiply by 0. But you can multiply by any, now that's the entire equation, okay? The left-hand side and the right-hand side. You can't just multiply one or the other, the whole equation. Now, I also like to say it this way, because I think more in these terms. Multiply or divide by any non-zero constant. Why would you not divide by 0? Undefined, completely undefined. So I like to say multiply or divide, because multiplication and division is just reciprocal relationship, so it's fine. Now, and that makes sense too, because that doesn't change the meaning of that equation, so it certainly would produce an equivalent system. Now this is the one you might find, well, why would this work? But you add a multiple of one equation to another. Okay, now let's see, does that make sense? If you multiply this equation by something, it's an equivalent equation, and then add it to this one, the system stays equivalent. Now, if you think about it, that's what we did when we did solution by, what do we call it? Elimination by addition. That's what we're doing. Multiply this one by something, add it to the other one. That was one of the steps that we could do. So sure enough, that also produced an equivalent equation. And those will take care of everything we ever need to do. Okay? Now, here is a definition I don't think we've hit before. It's, and they just sort of sneak it in here, rewriting a system of linear equations in row echelon form. Okay, what in the world do we mean by row echelon form? We haven't hit that, have we? I'm pretty sure we haven't. Okay, so here is sort of a definition here. They're going to give a little bit better one, I think, a little bit later. Row echelon form. Okay, row echelon form. Not a phrase I ever use anywhere other than linear algebra, okay? Okay. It says it usually involves a chain of equivalent systems, each of which is obtained by using one of those three techniques, basic operations. That process is called Gaussian elimination. Now, it's bugging me that they have not defined it. This, I guess I've never noticed that before. They go in great detail on row echelon form of a matrix, but we haven't even mentioned that yet. So why do they mention it here but not tell you anything about it? Okay? Now here's what we mean by row echelon form. We're going to get to it in the next section when we're talking about matrices, but we haven't even introduced the term matrix yet. So row echelon form will basically be, if you look at the previous page, page 6, how you had the first equation and first system, 3 equations, 3 unknowns, and you had a rectangular system. But then when you did the second form, which was equivalent to it, you had an x up here, and then y, z's and equal. Here you didn't have an x, but you had y, z and equal. And here you didn't have an x or y, but you had z and equal. That's row echelon form. And basically what it means is there's a couple of features to it. And the first one almost makes no sense now, but I'll say it. If you have a row of all zeros, it's at the bottom. If you have a row of all zeros, there's nothing in the row. So, but later we'll hit that. Then the next feature is the first non-zero entry that you have in the first equation, the coefficient needs to be 1. And that's why it was an x in that first one. Okay? Then, the first non-zero entry in any row is going to be a 1. But those leading ones will be stepping to the right as you go down. So you wouldn't have a leading one here and there and there. You know, that you row echelon form, the first one is a 1 here, and then you have zeros below it. The first non-zero entry here will be a 1, the zeros below it, 1, the 0. As long as you have anything below it, it's going to be a 0. That's row echelon form. The leading entry in each row has a coefficient of 1, and those one step to the right as you go down. Okay. You may skip something. That's okay too. But we'll see. So it bugs me. They mentioned row echelon form, but that didn't define it to you. Okay, for you. Now, that process that we're going to be using is called Gaussian elimination. Okay. Now, this is named after Carl Friedrich Gauss, a German mathematician. He's often recognized with Newton and Archimedes as one of the three greatest mathematicians in history. That's pretty good company. Now, my pre-calculus, which was algebra trig this morning, we mentioned Euler. Algebra it was. Okay? Euler was one of the most prolific mathematicians of all time. And but Gauss was considered one of the greatest because of all the things he came up with. Now, interesting little note here, although this method is named in his honor, the Chinese used an almost identical method some 2,000 years before Gauss. We are pretty ignorant of what happened in the rest of the world. But anyway, so what we're going to do now is use those three operations to change that first system of equation we had on page 6 to the second, okay? And we'll go over that in gory detail, okay? So here is your original system. X minus 2y plus 3z is equal to 9 minus x plus 3y is equal to minus 4, and 2x minus 5y plus 5z is equal to 17. Now, we want to solve it. Now, I want to remind you of the features of row echelon form. Okay? First, if you have any rows, zeros are at the bottom. We don't, or if they are, you can't see them because they're not there. Okay, whatever. Okay. Now, the next feature is the first non-zero entry in the first row we want to be coefficient of 1. We've got it that way already. That coefficient is 1. Now, if this row were up here and this one down here, you had one of two choices. One choice would be multiply this row by a minus 1, and then it would have a coefficient of 1. Or exchange the two rows. If this row had been up here and this one somewhere else, then the best choice, you could divide everything by 2, but that gives you a bunch of fractions. I don't like fractions. So I would just flip rows. So if you had a system and only one of those had a leading coefficient of 1, but it wasn't at the top, but yeah, remember, that's that was our first. You can exchange any two rows anytime you want. That gave an equivalent system. This one has right what we need. So we're happy, very happy counters. Now the next thing we want is to eliminate these two coefficients. A lot like we did with elimination by addition. Only it's going to be really easy now because that coefficient is 1, so you'll do that by multiplying this row by some number and adding to that row. But this one is really easy, because all you have to do is add those two rows together. 1 times this plus that, that'll eliminate the x. So that's going to be our next step. Okay? And I'm going to write it over here. Equation 1 plus equation 2 becomes the new equation 2. That's that third operation, adding a multiple of one row to another row, multiple of 1, okay? So then the next equivalent system, we're happy with that first row, or first equation, so we're going to leave it alone. X minus 2y plus 3z is equal to 9. Okay, adding these two together and making that the new second row, what's x minus x? 0. So leave that alone. Negative 2y plus 3y. Why not? Okay. And 3z plus 0 is 3z. Be sure you put your plus sign there. And then 9 minus 4 is 5. Okay? Now, we've got the second and actually third thing that we wanted to happen. Well, maybe somewhere down the line. We wanted zeros below that leading x, the leading coefficient of 1. So we got that one. We want this to become a 0 as well. So how do we make that happen? Using our three operations. Yeah, that third one is what we're going to use most of the time. So if you multiply the top equation by a minus 2 and add it to this one, you'll eliminate that 2x one. Just like we did elimination by addition. So let's do that. Minus 2 times equation 1 plus equation 3 becomes the new equation 3. That's that third step, adding a multiple of one equation to another equation. Okay? So, let's do it. Negative 2 times x is negative 2x, plus 2x is 0, right? Negative 2 times negative 2y is 4y minus 5y would be minus y. Okay? Negative 2 times 3z is negative 6z plus 5z is negative z. And negative 2 times 9 is negative 18 plus 17 is negative 1. Okay, good deal. Now, we've got our next feature done. First feature we wanted was the leading coefficient to be a 1. Next feature is that first variable have zeros underneath that leading coefficient of 1. Okay? Now, the next thing we want to happen is in the second equation, the leading coefficient to be a 1. And we got it. And it's stepping to the right, so that's great. The next thing we want to happen is the one below that to be a 0 as well. How do we make this one become a 0? Using this. Add them together. Perfect. So that would be equation 3 plus equation 2 becomes the new equation 3. I think I said it backwards. Equation 2 plus equation 3. It doesn't matter. You're just adding them together. So, and these are equivalent because all our steps have been equivalent. So it's x minus 2y plus 3z is equal to 9. We're leaving this one alone now. Y plus 3z is equal to 5. And let's do that third step that we just did. What was it? I think I've done something wrong, haven't I? No, we're right. Okay. Go ahead. What do you get there? Oh, yeah, we're right. You would have an x, you wouldn't have a y, and so you wind up with 2z is equal to 4. Okay. So far, so good. Leading coefficient 1, 0 is below it. Leading coefficient 1, 0 is below it. But what are we missing here? Yeah, you have a leading coefficient of 2. How do we make that a 1?
Yeah, because you can multiply it by -1 and add it to the equation 2.
Okay. If you did that, now you wind up with y back down here. Don't do that. Okay? What was your second operation? Right. Can you think of a non-zero constant? Does that make that? Oh, yes, so 1/2. Or, as I like to say it, divide by any non-zero constant. That would be dividing by 2. Whichever you say, it's the same thing. So we'll do equation 3 divided by 2 is the new equation 3. Okay, so you have x minus 2y plus 3z is equal to 9. Y plus 3z is equal to 5. And now what happens when you do this one? Z is equal to 2. Now that is the one that I like the best, because it gives you part of your answer right there. Z's got to equal 2. Now, remember what we called this part before? Back substitution. So move up one row and say y plus 3 times 2, because z is equal to 2, is equal to 5. 5 won't write. Come on, you can write. Okay. I would probably write over itself, but who cares? Okay. Solve this. That would be y plus 6 is equal to 5. What would y be? Y is equal to -1. Okay? Okay. So now we got 2/3 of our answer. Now we can back substitute into the top one, and that is x minus 2 times a -1 plus 3 times 2, because z is equal to 2. Why my pen isn't writing, I don't know. And that's supposed to equal to 9. So this will be x plus 2 plus 6 is equal to 9. Can you figure out what x is? X equal 1. There you have your solution. It's the ordered triplet, 1, 2, minus 1. And that's what we got before. That's what we got with the thing. And by the way, this form that we did here was exactly the form we had in example 6. And we have already, that was the right-hand side on the top of page 6. That's how you do using elimination to rewrite a system in row echelon form. Okay? It's Gaussian elimination. Gauss came up with this idea, and that's what he got. Now, they have a weird-looking figure 1.2, and you have to really be careful looking at it, but basically each of these equations with 3 variables defines a plane. Here's a plane, there's a plane, and then some other places a plane, and there's only one point of intersection, and that's at 1, -1, 2. Except for showing off the graphics, I don't see anything that gives us. Okay, now maybe you can get something a little later, and we will, but that has one unique solution. And remember, anytime you're solving a system of equations, you're going to have one of 3 cases. One and only one solution, infinite number of solutions, or no solutions. Okay, and we'll see the graphics on those 2. I'm not going to draw them. I'll guarantee you that. Okay. It says, because many steps are required to solve a system of linear equations, very easy to make arithmetic errors. I usually have a pretty easy time doing that anyway. Okay, so you should develop a habit of checking your solution by substituting it back into the equation of the original system. But I had already done that. Remember, we did that last time. we plug that solution back into this equation and that equation, and it worked in both of them. Okay, so we did. Now, we're going to look at another system of equations, and we're going to try to row reduce that. And we're going to see what happens here. So here's the system. x1, I like it already, minus 3x2 plus x3 is equal to 1. 2x1 minus x2 minus 2x3 is equal to 2. And x1 plus 2x2 minus 3x3 is equal to negative 1. All right, we want to solve that. What would be, what do you look for first? And what do you want it to be? And is it? Yeah, okay, yeah, but all we're interested in is that top. First equation, leading coefficient to be 1. Okay, it is, we're happy campers, we move on to the next. What's the next thing we want to happen? Zeros and both of the equations under it. So let's deal with the second equation first. How do you get that 2 to become a 0? Okay, no, okay, you use that first equation, okay? Multiply it by negative 2 times equation 1 and add it to equation 2, okay? And that results in a new equation 2. You don't want to fiddle with that first equation. You're going to use that first equation. That's exactly like you want it to be. So this first, oops, Freudian slip here, okay. I didn't know he wore slips, never mind, okay. So anyway, write that first equation down. You have that leading coefficient being 1, write it down. You're happy with it right now. X sub 1 minus 3x sub 2 plus x sub 3 is equal to 1. Now, if you might notice, this is a lot of writing the same stuff over and over and over, which makes it longer and more tedious. We're going to come up with a technique to help that a little bit, okay? But keep in mind that's what we're doing. Okay, now let's do this rule to see what happens with equation 2. So what do we do? Minus 2 times 1 is, times x1 is negative 2x1 plus 2x1 is 0. That's exactly what we wanted. Now negative 2 times negative 3x2 would be 6x2. Wait, I'm supposed to subtract x2 from that, sorry. I got carried away. 5x2. Okay. And then negative 2 times x3 is negative 2x3 minus 2x3 is minus 4x3. Perfect. And then last, 0 equals 0. Didn't see that coming, but it's okay. Nothing wrong with that. Okay? What do we want to happen next? Yeah, the third x1, you want it to be a 0. Okay? Or you want the coefficient to be a 0. So how do we make that happen? Using the first one. Yes, minus equation 1 plus equation 3 is the new equation 3. Okay, do it to it. Zero, okay, because minus x1 plus x1 is 0. Next. 5x2 minus 4x3 is equal to negative 2. Now, I don't know if you like looking at forests and trees, but I want you to look at the forests here, not just the trees. Look at the big picture here. What is that saying, especially those last two equations?
The last two are the same, but they equal different.
And how many times can that happen? How can the same thing on the left-hand side be different things on the right-hand side? It can't. Okay? It can't. Whatever it is here, that 5x2 minus 4x3, it can't be 0 and at the same time be minus 2. It just can't happen. So this would be, what would you think? No solution is certainly one correct answer. Okay, to that system of equations. But what could you call that system of equations? We were calling them earlier, if it had no solution, an inconsistent system. This is an inconsistent system. I can't write. Okay, inconsistent system. There is no solution to that equation. Now they took it one more step. They didn't look at the forest, they looked at individual trees. And they didn't even do it the way we were supposed to do it, but they just looked at this and say, well, if you multiply this one by minus 1 and add to that, you get 0 plus 0 equal negative 2. 0 can't equal negative 2. Not in this universe, okay? So we don't want it to, okay? So that tells you, anytime you have a situation that cannot exist, no solution, inconsistent system, okay? Now, the graph doesn't help me a lot here, but it is true, but it's such a messy graph, it's hard to see. These inconsistent systems, if it had been, well, I'm going to say the first case, you would have recognized it, I think, automatically. If you have three planes and they're all parallel to each other, that's an inconsistent system. It's like two lines parallel, two planes. But this has yet something a little more insidious. These aren't parallel planes, but the intersection of this plane and that plane is a line. Any two planes, if they intersect, it's going to be a line. And then if you do either one of those planes with the third plane, it also makes a line, but it's parallel to that other line. So those two lines never cross. That's an inconsistent system as well. You have to really look at it here to see that. But as you see the sort of the purplish kind of plane intersecting the greenish kind of plane, that's that line that heads downhill, you know. And then the greenish plane intersecting the pinkish plane, that's the line just above it. And those two are parallel lines, they never intersect. Now, okay, I'll leave it like that. Those two lines never intersect, so there can't be a point in common. Okay, let's do another one. I think I will erase. I was going to try to do it on the last part of the slide, but just in case things get a little hairy, let's do it. X sub 2 minus x sub 3 is equal to 0. X sub 1 minus 3x sub 3 is equal to minus 1. Minus x sub 1 plus 3x sub 2 is equal to 1. All right. It says solve that system. What would be your first approach? What you want? What would be your ideal situation here? Yes. And the first equation doesn't have it. So what's the legitimate move you can do? Flip them, exactly. So our first will be equation 1 and equation 2 interchange. Okay. So the next equivalent system will be x sub 1 minus 3x sub 3 is equal to minus 1, and x sub 2 minus x sub 3 is equal to minus 1. No, wait, is equal to 0. Huh. Wait a minute, yeah, I'm sorry. I got lost in the sauce there. Okay. I couldn't see the tree, okay. And then the third equation can remain minus x sub 1 plus 3x sub 2 is equal to 1. Good. All right. So you managed to manipulate it so you had the first the first leading coefficient to be a 1 in the first equation. You did that by flipping the 2. Okay? Done. You didn't even have to multiply anything. It's automatically. It was already a 1. Okay, done. What you want to happen next? The x of 1 in equation 3. Because you already have a 0 in equation 2 there, so all we want is to make that a 0 there. How will we make that happen? Using equation 1. Second? Yeah, equation 1 plus equation 3 is the new equation 3. All right, let's do that one. So 1 stays the same, x of 1 minus 3x sub 3 is equal to minus 1. Equation 2 stays the same, x sub 2 minus x sub 3 is equal to 0. And what's your new equation 3?
There's no x sub 1.
Right.
Plus
3x sub 2
minus 3x sub 3.
okay, is equal to
0.
Yeah, you're right. It's 0. Okay? Now, step back a little bit. What do you notice about those two equations? The last two.
If you take out this one multiple, take out 3, it will be the same as 3.
Exactly. Okay? One of those equations, the third one, is exactly 3 times the second one. Okay? Which means if you go to solve it, and you could do that, you can solve it if you want to. What you just said was a very legitimate move. Divide the third equation by 3, and you get x of 2 minus x of 3 is equal to 0. That's exactly that. Add those two equations together, and you get 0 plus 0 equals 0. When is that true? Always! Okay. So that means you have an infinite number of solutions. It is a consistent system, but it has infinite number of solutions. And what you can do there is parameterize, because what operation I just suggested would eliminate this and have a row of all zeros at the bottom, which is what you want in row echelon form. And then you could just parameterize this and say let x3 be t, so x2 is also t, and x1 would then be -1 plus 3t, right? And then with those as your ordered triplet, pick a t and t and come up with an infinite numbers solution, right? Okay, they didn't go so far. Yes, they did. They said x of 1 is equal to, let's do that again, x of 1 is equal to 3t minus 1, x of 2 is equal to t, and x of 3 is equal to t. So your ordered triplet would be 3t minus 1, comma, t, comma, t. Okay, where t is any real number. So negative 1, 0, 0, that should work. 2, 1, 1 should work. 5, 2, 2 should work. Negative 4, negative 1, negative 1. I mean, infinite number of solutions. Okay? When you get it in parametric form like that, it's real easy to figure out what they are. Now, they have this little discovery at the bottom of the page, and it looks like it's not going to take too long, so let's see what it is. You'll have to keep me up with time. How are we doing? Is what?
44 more minutes.
Oh, plenty of time. Okay, I hope. Graph these two lines represented by the system of equations. Okay? Here is x minus 2y is equal to 1. Okay? Okay. How would you choose to graph that? Move your x over, is that what you said? And yeah, I think I know where you're heading on this. So you subtract x from both sides, is that what you're saying? And that gives you minus 2y is equal to minus x plus 1, negative 2. So that would give you y is equal to 1/2 x minus 1/2. And what would you do with that? Okay, so you go down here. Is that where you're meaning? Yeah. Okay, 1 over 1/2. So you go up 1 for every 2 you go to the right. No, wait. Up 1 for every 2 you go to the right. So that would be here and there, here and there, here and there. And down 1 for every 2 you do to the left, and something like this. Okay, so there would be your approximate graph, I hope I've got it right, of that first equation. Let's do the second in a different color. You give me a color. I sort of figured you were going to say that. Are you a Tar Heel fan?
It looks better when you have dark and light color.
Right. Okay. Yeah. The second equation is minus 2x plus 3y is equal to negative 3. Okay. How would you proceed with that one? Okay, so add 2x to both sides. And that would give us, that goes to 0. 3y is equal to 2x minus 3, right? Divide by 3, every term by 3, and that would give you y is equal to 2/3 x minus 1. And what does that tell you? Y-intercept is -1, got it. Up to right 3. Now, I think it's that point right there. Up to right 3, down to left 3, and down to left 3. So I think that is that equation. Now, my lines don't make a lot of sense, but I think that's the point in intersection. Okay. And it looks like the answer is 3-1. All right. Now, it says use Gaussian elimination to solve this system. So, let's go to a clean page and do that. Here's, let me go back to black. Okay. X minus 2y is equal to 1 minus 2x plus 3y is equal to minus 3. Okay, Gaussian elimination, what would be your first thing you look for, or you want to happen, want to be there?
Let's talk about the equations below the number 2.
I think they just skipped some steps, is what they've done. Okay? So let's us not skip steps, because that was confusing. What's the first thing you want to happen?
Make that -2x.
In other words, you got the 1 there where you want it, so you're happy with that, and make the minus 2x a 0. How do you make that happen?
Multiply
2 times equation 1 plus that's equation 1 plus equation 2 is the new equation 2. So since we're using the top equation, let's leave it alone and have x minus 2y is equal to 1. And what would your new second equation be? Okay, negative 7y. Let me see. I kind of got lost in the sauce there. That would be a 0, and then, I'm not sure that's right, is it? Negative y, okay. I'm not as lost as I thought I was, okay. Next. -1 is equal to -1. Okay? What would be your next step? Yeah, I'm going to do it that way, okay? Y equal 1. Okay? And then plug it in and you get x minus 2 is equal to 1. X equals 3. And what do we get before? Whoops. X equals 3, y is equal 1. Sure enough, that's what we got. Okay? The ordered pair was 3, 1. Just like we saw before. However, my graph didn't look like they crossed there, but it's just because my graph was pretty lousy looking at that. Don't be laughing. Okay. So, now it says graph the system of equations you obtain at each step of the process and what you observe about the lines. I really don't want to do that, so I don't care. Okay. So let's leave that alone. Homework exercises here would be any of the odds 1 through 5. They're all at Calc Chat. Any of either 7 or 9, they're both at Calc Chat. Any of the odds 11 through 23, they're all at Calc Chat. Where 21 and 20, 19, 21, and 23 both look fairly interesting, don't they? Any of the odds 25 to 29. Any of the odds 31 to 35. Any of the odds 37 to 55. And either 57 or 59. Those both look pretty interesting, don't they? Either 61 or 63. 65 is legitimate to do. They're found at Calc Chat. 67 is a true false. It should be found at Calc Chat. And 69 is one that should be found. Oh, yes, at Calc Chat. 71 or 73 should both be found at Calc Chat. 75 should be found at Calc Chat. Any of the odds 77 to 81 should be at Calc Chat. 83 should be at Calc Chat. 85 says it's a writing exercise, so if you want to do that, you can. 87 should be at Calc Chat, and 85 should be at Calc Chat too. 89 should be at Calc Chat, and 91 should be at Calc Chat. All right, good deal. Any questions? All right, let's move on to 1.2. Okay. 1.2 is going to introduce a concept, a term, what we're going to do the rest of the term almost, and that is using a matrix. Okay? Now, Section 1.1 introduced Gaussian elimination as a procedure for solving a system of linear equations. In this section, you'll study a procedure more thoroughly, beginning with some definition. That first definition is that of a matrix. A matrix, if you have any grouping of M, okay, M and N are both positive integers. Okay? 3 by 4, 7 by 15, any two positive integers, okay? So we'll call it M by N, okay? Now that doesn't mean you multiply them together. It means M rows, N columns, okay? That's what we mean. So it forms what we call a rectangular array. An array is any real numbers organized in a rectangle. Okay, so here is a matrix. A11, A12, A13, dot, 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 A1, M. A21, A22, A23, dot, 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 up to A2 sub M. A31, A32, A33, dot, dot, okay, up to A3. Okay, I'll make sure I had my variable right. No, I didn't. These are n's. That's why I stopped and paused, because I said that doesn't seem right. These, I think, are n's. Now, why n? We haven't gotten there yet, but I did say it. M rows, N columns. So your N is counting the number of columns you have. So that should be an N there. And then we're going to dot, dot, dot this down the page, and this down the page, and this down the page, and this down the page, this across the page, this across the page, wherever we need to go here. Your last entry will be A sub M1, A sub M2, A sub M3, dot, 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 up to A sub Mn. Now, you put that array in brackets, and this is what we call a matrix. Now, all those entries are generally real numbers, okay? Your subscripts have to be positive integers, but the entries could be anything. They don't have to be integers, they don't have to be positive, they don't have to be rational. Yeah, I mean, there's nothing requirement of them except they be real numbers. Okay? The first subscript indicates which row you're on. First row, second row, third row, fourth row, fifth row, sixth row, or nth row. The second subscript indicates which column you're in. The first column, the second column, the third column, all the way across to the nth column. Okay? Now, just like we've seen with the equations, some of these entries may be zero, so there may not be anything there, but that's just counted as a zero entry. Okay? Remember, they can be any real numbers, and zero is a real number. All right. And sometime we'll refer to this as the entry Aij, where I is some number between 1 and M, and J is some number between 1 and N. An M by N matrix has M rows, N columns. Matrices are usually denoted by capital letters. Okay? And by the way, if you haven't picked up on this, the singular is matrix with an X, and the plural is matrices with a CES. Okay? I guess that's I'm guessing Greek, but it could be Latin. I don't know either language, so I don't know. All right. So what the Aij represents is the real number that is in the location of the ith row and the jth column. Okay. So that's what that Aij stands for. I is called the row subscript, J is called the column subscript. Now, and we say that that matrix has size M by N. We don't multiply the two numbers together, we call it M by N. 7 by 2. We don't say 14, we say 7 by 2. Okay. Now, a matrix with M row, if M is equal to N, the matrix is said to be a square matrix of order N. Okay, if M and N are the same, then there's a square matrix of order N. Now, if you have a square matrix, you can talk about those entries that go down like this. And notice A sub 1, 1, A sub 2, 2, A sub 3, 3, A sub 4, 4. Those entries are A sub I, or JJ, or whatever you want to call them. These are called the main diagonal entries, going upper left to lower right. That's the main diagonal. There is a other diagonal, but we never, or seldom, will ever use that. Okay. So, how are we doing on time? 5 minutes. Okay, let's do example 1. Each matrix has an indicated size. This is almost silly, but let's start that. Here's a matrix. What's the size of that matrix? No? Size is 1 by 1. The size is always that. Okay? Here's a matrix. What's its size? Two by two. Even though it hasn't got a single entry of any value, it's still a 2 by 2 matrix. Okay? How about this matrix? E to negative 7 pi root 2 4. What's its size? Say that again. 2 by 3. Okay, because there's 3 entries. E and pi and root 2 are real numbers. They're just irrational numbers. So it's still a 2 rows, 3 column, 2 by 3 matrix. Now, what does this have to do with what we did in section 1.1? Well, one common use of matrices, now this isn't the only use, but it's a common use of matrices, is to represent a system of linear equations. And to do that, we have 2 matrices, or maybe you want to say 3 matrices involved. Okay? Here's the system that I'm going to represent. X minus 4y plus 3z is equal to 5. Minus x plus 3y minus z is equal to negative 3. And 2x minus 4z is equal to 6, I think it is, yeah. All right. That's a system of equations. Here is a matrix that represents that system of equations. Lose the variables. Lose the equal sign. That matrix is then, what would you guess it to be? Got it? Two what? 2, right? 0. Okay, that is a matrix that most closely aligns itself with that system of equations. But this is what we call an augmented matrix. It's actually made up of 2 matrices kind of pieced together in some way. The first of those matrices is your coefficient matrix, which is basically the 1, negative 4, 3, negative 1, 3, negative 1, 2, 0, negative 4. That's called the coefficient matrix. And if you add that column vector to it, what that's equal to, just when I say add it to it, attach it to it, this is an augmented matrix. Now, back when I first learned linear algebra, we actually would put a dashed line in there to indicate the coefficient matrix and the solution vector and make the augmented matrix. I notice they don't do that anymore. Part of the reason might be I actually found myself doing this. If I made those dashes a little bit bigger and evenly spaced, you may almost think there are extra 1s in there. They're not, so they typically don't do that anymore. So this is called the augmented matrix. That's called the coefficient matrix. Okay. How much time? 1 minute? Okay. I think I can get this done in a minute. Okay. Okay. In the last section, we talked about solving a system of equations using equivalent matrices, and we had what we call we may not have called it that. We just called them operations. Interchanging two equations, multiplying an equation by a non-zero constant, I said multiplying or dividing, and adding a multiple of one equation to another equation. In terms of matrices, we call these elementary row operations, not equation operations. And they come out being the same. And that leads to row equivalent matrices. Just like we had row echelon equations, we now have row echelon matrices. So here are the elementary row operations. Exchange any two rows, just like exchanging any two equations. Multiply any row by a non-zero constant, or multiply or divide, and add a multiple of one row to another row. And remember when I said this equations, we were writing a lot of things over and over. For instance, the variables and the equal signs, you forget the variables and equal signs. So it makes it a little shorter, but the operations are identical. So we'll begin next time with doing some elementary row operations on example 2. Okay. Now, we probably did get just barely far enough along to have, and this is a long section too. You can do any of the odds 1 through 5. That's just naming the size of a matrix. If you wanted to try to start 7 or 9, you can. That's sort of to me, almost a useless set of exercises there. And stop there. If you don't even have to do 7 or 9 if you don't want to, but you can take a look and see, and we'll pick up and go from there. Hey, all right.